So for number 2, we're going to start by drawing ammonia, NH3. So let's look at what are the electronegativity values. So we have nitrogen, and then hydrogen. 3 hydrogens. So each of the hydrogens we know is 2.2, right? We have these memorized. Nitrogen has 3. Remember that there is a pattern on the periodic table. With lithium, it starts with 1 and then increases by 0.5 as you go to the right of the periodic table. So are there bonds between the nitrogens and the hydrogens? Are these covalent? So let's look at the electronegativity difference. So 3 minus 2.2 equals 0.8. That's the delta electronegativity. And this is less than 1.5. If it is less than 1.5, the difference, then it is covalent. Okay, so how many valence electrons are there? So nitrogen, if you look on the periodic table, has 5 valence electrons. So this is part D. 5 valence electrons. And then each of the hydrogens have 1. So that gives us 8 valence electrons. So is this a hypovalent, hypervalent, or an octet? Well, in this situation, this will be an octet because nitrogen will want 8 electrons. So will there be multiple bonds or resonance? No, there will not be because we know that the Lewis dot structure of ammonia looks like this, right? So there's no resonance structure, single bonds. You only have resonance structures when you only have potential resonance structures when there are at least double bonds. Not with single bonds, you don't have resonance structures. So let's see, what is the two-dimensional Lewis dot structure? Oh, so basically we have already drawn it here. And so if we want to see how many electron-rich regions there are, let's just look at how many regions are around nitrogen. So we have 1, 2, 3, 4. 4 electron-rich regions around the nitrogen. Okay, so what is the electron geometry? So if there are 4 electron regions surrounding the central atom, we call this tetrahedral. So remember that even the lone pairs, that counts as an electron-rich region. Each lone pair counts as an electron-rich region. So what is the hybridization? So as I said in the earlier question with water, if there are 4 electron-rich regions, a good trick that I use to remember is, if it's 4, it's sp3, because pretend S has 1, so 1 plus 3 equals 4, so 4 electron-rich regions, so sp3. So what is the bond angle in this tetrahedral structure? It's going to be around 109.5 degrees. Maybe a little bit less because of the electron pairs, which will be pushing the other regions. But that's okay. So around 109.5 degrees. How many bonding pairs are there? Let's count. So there's 1, 2, 3 between each of the hydrogens. So there are 3 bonding pairs. How many unbonded pairs are there? There's 1 unbonded pair of electrons. So that's going to be 1 unbonded pair. Okay, so what is the molecular geometry? So if there's 3 bonded pairs and 1 unbonded pair, we're going to write it like this. So a central atom with 3 bonded pairs and 1 unbonded pair. And so what is the Vesper structure, the 3D structure of ammonia? So in a tetrahedral structure, think of it kind of like a tripod kind of structure. So let me show you. So the wedge, the dark wedge, symbolizes that the hydrogen that hydrogen is protruding out of the page, whereas just the line indicates that it's on the page. Think of the hydrogen on the plane of the page, and while this dotted wedge, this signifies that it's behind behind the paper. So now you can think of the structure as kind of like a tripod, and then you have the unbonded electron pair at the top. So let's draw with the dipoles in this molecule. So we know that nitrogen is the most is more electronegative than hydrogen, right? Hydrogen is 2.2, nitrogen is 3. So all of our arrows are going to be drawn towards nitrogen. Right, and the difference is 0.8, right? 3 minus 2.2 for each of them, 0.8. So definitely there's going to be a net dipole. How many sigma bonds or pi bonds are there? Remember, sigma bonds are single bonds, pi bonds are double bonds, right? So the ammonia only has 3 single bonds. That means that it has 3 sigma bonds. How many, is it polar or nonpolar? Well, because we said that there was a net dipole, right? Think of all these dipoles. The resultant dipole, there's going to be a resultant dipole. So if there is a resultant dipole, then this molecule is polar. And indeed, ammonia is polar.